what is so special about vector databases? Why do we need, additional type of database, and what we can get from it? What are the main use cases for vector database in general?
Yeah, great question. I'm going to talk about vector databases from two different perspectives. One is more from an old school perspective, so from before ChatGPT, before large language models, before autoregressive models. And I'm going to sort of talk about it a bit more from a new school perspective as well, from a modern perspective, quote unquote. And it feels very, very strange to say this because vector search has actually been around for a long, long time, right? If you talk about a lot of the if you talk about, for example, SIP features and you talk about descriptor matching, all of that is pretty much vector search, originally using KD trees and other data structures. But vector search, as it relates to deep neural networks, as it relates to deep learning, I would say it really hasn't been around for that long. It's been around for probably about a decade, and starting off with, well, I take that back. It's been popular for about a decade, starting off with when folks discovered that you could really, these embeddings from deep neural networks, from trained convolutional neural networks, were very representative of your input image or of your input video or audio snippet or any other type of unstructured data that's out there. So early on, vector search and vector databases were used primarily for things like recommendation. So you can imagine if I have, if I'm, a big e-commerce website, I have all these products or pictures of products, and I have a purchase history. Maybe I want to find similar products to those, not just by, hey, who's selling the product, or not just by the title of the product or the description of the product, but also by pictures, videos of that product as well. It's one of the ways that we can do recommendations with semantic matching, semantic recommendation. There's also other things like fraud detection that vector databases were used for. There's AI drug discovery and a wide range of other retrieval and search applications as well. It's really traditional. That's what vector databases in traditional sense, in more of an old school sense, right?
And Frank, so based on this description, like, I assume that it is like looking at the just raw API, like there are primitives behind it. We have a vector and we want to find, and in the database we have a lot of other vectors, and we want to find a similar vector, right?
Yep.
Like whatever it means based on some distance metric.
That's right. Yep.
What about would it be something that you would also use for anomaly detection to maybe to figure out, okay, actually yeah, you will find the closest and it is far, then maybe it's anomaly.
Absolutely. Yeah, for anomaly detection. And for anomaly detection, fraud detection, or anything along those lines. And I'll sort of explain, I think it's probably a little bit prudent of me to take a quick step back and explain how vector databases and how these embeddings work in general, right? And I don't want to limit it necessarily to trained neural networks, but I'll use trained neural networks as really the backbone here. And if I have any type of if I have any type of neural network, it could be, one of the more modern transformer models, it could be an old convnet, and I look at these, typically one of the latter layers or one of the outputs of the later layers. The result of that is typically, is a high dimensional tensor known as an embedding. And long story short, I won't dive too deep into it, but the more similar or the more relevant, more semantically related that your input data is, the closer these embeddings are going to be to each other. I use this example all the time. I've been using this example for like a year and a half at this point, where if I have two pictures of German Shepherds, my favorite kind of dog, these pictures, they could be with different backgrounds, they could be, doing different things, but with a neural network that's trained to classify, let's say, different breeds of dogs, these embeddings would be very, very close to each other after I run these two images through my trained machine learning model. And the reason is because that model has been trained to pick out the specific breed of the dog, right, in your input image, and really ignore a lot of the other auxiliary information.
If we are talking about object classification.
Exactly. classification or detection to a certain extent as well, right? And again, I'm simplifying things significantly, but that's the general idea, is that you have these high dimensional tensors which are extremely representative of your input data, and it extends to beyond images as well, right? It extends to natural language, it extends to audio, to video, any type of human generated data. There's a recent paper from Meta called ImageBind, and they actually embed IMU data into the same space as image data as well, which is really, really quite fascinating. I recommend all the listeners go take a look at that ImageBind from Meta. And that's the core principle. This is the idea that embeddings, which are closer to each other, means that the data is more relevant in some way, shape, or form, depending on how your model is trained. That's the core principle that vector databases use. That's the core principle that vector databases leverage, right? And really, what vector databases are meant to do is they're meant to store, index, and search across these vast quantities of human-generated data or unstructured data using their embedding representations. So you can imagine this way, right? So if I have, going back to your example, Peter, about anomaly detection or fraud detection, if I'm a big bank and I have all these transactions, right? I have tons and tons and tons of transactions. One of the interesting use cases that I can use a vector database for is I can actually turn those transactions, details about those transactions, into an embedding, right? Into an embedding, and I can search in my vector database for nearest neighbors. And if most of those nearest neighbors correspond to, or let's say 98 or 99+% of those nearest neighbors, if they correspond to valid transactions, non-fraudulent transactions, then I know that my transaction, this new transaction, is probably also non-fraudulent. I'm pretty confident, right? I'm very, very confident. But if any of these nearest neighbors, if I have, let's say, greater than 5 or 10% of my nearest neighbors are fraudulent, then I probably should run this particular transaction through a larger machine learning model, one that is trained specifically to do fraud detection, to figure out whether or not this is truly fraud. So you can think about how vector databases work from not just the perspective of images, video, audio, text, but really for any type of data that you can't put into, let's say, MongoDB, or any type of data that you can't put into a wide column store or in a relational database, right? The paradigm is always the same, is that you take the embedding representation and you search for nearest neighbors.